Today we're going to continue on with Chapter 13 on gravitation. Alright, so we want to talk about gravitational potential energy. We've talked about, gravitational potential energy before in the sense that U is equal to mgh. Right, but there's a little more to it when you have multiple objects. Alright, so the gravitational potential energy of a two-particle system, let me just get this out of here, is going to be given as such. So it's the potential energy U, and we could give it a subscript G if we wanted to, is going to be minus capital G m little m divided by r. So this looks very close to Newton's law of gravitation for force. In a second we're going to see how we get to this equation. However, what it's saying is that the potential energy is going to be the negative of the gravitational constant times both the masses divided by the radius between them. Right? So the further an object gets away, the less potential energy it's going to have, or the less negative the potential energy would be. So as the potential energy approaches zero, as r approaches infinity, and for any infinite value of r, the value of ur is going to be negative. So if the system contains more than two particles, so let's say you had a system over here with three particles, you need to consider each pair of particles in turn, calculate the gravitational potential energy of that pair with the above relation, as if the other particles were not there, and then algebraically sum the results. All right, so basically you would find the relationship between these two masses, between these two masses, and between these two masses. All right, and then you could just add them together. So what that would look like is the total potential energy is going to be equal to the negative of the first one. So the first relation is going to be m1, m2 divided by r1, 2, which is the radius between, or the distance between, the mass 1 and mass 2. And then you add that to g m1, m3 divided by the radius between 1 and 3, plus g m2, m3 divided by the radius between 2 and 3. So basically you would just add the potential energies together of each of the different relationships. Okay. So let's look at, let's shoot a baseball directly away from Earth along the path in the figure. So if I shot a baseball directly up, we want to find the gravitational potential energy U of the ball at point P along its path, which is a radial distance r from the Earth. So we're trying to find what the potential energy is here, and it's going to be a distance r away from the center of the Earth. Now, the work done on the ball by the gravitational force as the ball travels from point P to a great infinite distance from Earth. So if I took this object and I sent it all the way to infinity, the work done on the object would be given by, so the work is going to be equal to the integral from r to infinity, right, because we're going from this position, which is r away, all the way to infinity, times the force, and it's going to be the force as a function of r. So this is not force times r, this is going to be the force as a function of r, times dr. Right, this is our work equation. Well, if we look at f dr a little bit closer, so f dr is simply going to be f dr cosine of theta. However, the angle between these two vectors is 180 degrees because you have the force vector of gravity going down and you have the dr, which is going away from Earth, going up. So the angle between these two is going to be 180 degrees. So the cosine of 180 gives you a negative sign, gives you negative 1. So really this ends up being negative f dr. Alright, so then if I plug this back into our equation, our work is going to be equal to negative, because now we have a negative sign, F, and this is going to be the force due to gravity, which we know from Newton's law of gravitation. So we can go ahead and replace that with gmm, right, big M, little m. Big M is usually the mass of the Earth, little m is usually the mass of the particle, or in this case, a baseball. And then you would divide by r squared, and then you have this dr term. All right, so now we want to find what the total amount of work is. So we're going to have to take the integral. Excuse me. So this is going to be, keep the negative sign up front. This is going to be the integral from r to infinity of this whole thing. Now, most of these variables in here are constant, so we can pull those out. Or most of these values in here are constant. So this is going to be, the work is going to be negative g big M little m times the integral from r to infinity. And then inside the integral, we just have 1 over r squared dr. All right, so we're going to do the integral of this. Keep in mind there's a negative sign out front here, so when you do the integral, you get 1 over r, and then you pull out a negative 1, so that negative sign is going to go away. So you end up with the work being equal to gm little m divided by r, and that is across the boundaries from r to infinity. All right, so when you go draw that a little better. So when you go ahead and plug in your boundaries, you do the top minus the bottom. So we're going to take r as infinity here, and of course, if r is infinity, this value goes to 0. So this ends up being 0 is equal to, and then if you plug in r for this, you get, 0 minus the bottom, so it's gmm over r. So really, our work is equal to the negative times the gravitational constant times the two masses divided by r. Now, we also know that this is the amount of work required to move a ball from point r all the way to infinity. All right, so if I were to, and you could think of it in the opposite, so if I wanted to bring a ball from infinity to a point P, I would have to do positive work with the same magnitude. Okay. Now also work can be expressed in terms of potential energies, right? We know that there's a direct relationship between the two. We know that basically the change in potential energy is going to be equal to the negative work. All right, so the potential energy at infinity minus the potential energy at r is going to be minus the work, which means that, well, potential energy at infinity is going to be 0. So really this is just negative u is equal to negative w. The negative potential energy is equal to the negative work. So our potential energy is equal to work in this case, which is minus gmm over r. All right. So that gets us the equation we saw last slide, right up here. All right, so the potential energy is going to be equal to this equation here. All right, so let's talk about escape speed. Now, if you fire a projectile upward, there's a certain minimum initial speed that will cause it to move upward forever, basically allowing it to escape the pull of gravity. And on the Earth, it would allow it to escape the pull of Earth's gravity. All right, so theoretically, it's only going to come to rest at infinity. So this minimum initial speed is called the Earth's escape speed. So consider a projectile of mass m that leaving the surface of a planet that has mass big M and radius r with escape speed v. The projectile has a kinetic energy k, which is given by 1/2 mv squared, and a potential energy u that's given by our equation that we just saw. So this is u is equal to minus gmm over r. So when the projectile reaches infinity, it's going to stop and therefore have no kinetic energy. It also has no potential energy because an infinite separation between two bodies are 0 potential energy configuration. Right, so if this value was infinity, your potential energy would also be 0. All right, so its total energy at infinity is therefore 0, which means because of the conservation of energy, its total energy at the planet's surface must also be 0. All right, so for instance, this is going to be k plus u. Our kinetic energy plus our potential energy is going to be equal to 1/2 mv squared plus our negative gmm over r, and that must equal to 0. So at this point, I want to try to find what this velocity is. I want to find what this escape velocity is. So what I would do is, first of all, I can cancel some of these m's out, right? This m is going to cancel with, with that m. All right, so what you're left with, and if I move the 2 over to the other side, you get v squared is equal to 2g big M divided by r. Solve for v, and you see that our escape speed ends up being the square root of 2gm divided by r. So if I wanted to solve for what the escape speed was, all I would need to know is what the mass of the object is and what its radius is, or the radius away that the object happens to be. So in this case, the mass of the object would be the mass of the Earth, and then the radius would be the radius of the Earth. Or if you were above Earth, then that radius would be a little bit bigger. All right, depends on where you are. Okay. So just to give you some idea of what some escape speeds are, and notice these are given in kilometers a second, which is 1,000 times greater than what we normally use, which is meters a second. So, for instance, if I wanted to escape the Earth's moon, I would need to be launched off the surface at 2.38 kilometers a second. If I wanted to escape Earth's gravitational pull, I would need to be launched at 11.2 kilometers a second. For Jupiter, it's 59.5 kilometers a second. Right? And then it kind of goes up from there. I mean, the sun is quite large, and if you even look at something like a neutron star that is pretty massive, you end up with something like 2 times 10 to the 5th kilometers a second. All right, so these are the speeds that you would have to go, basically, to escape the pull of gravity and to end up with a final potential energy of 0, and kinetic energy of 0 as well. All right, so let's go ahead and do an example. So an asteroid headed directly towards Earth has a speed of 12 kilometers a second relative to the planet when the asteroid is 10 Earth's radii away from the center. Neglecting the effects of Earth's atmosphere on the asteroid, find the asteroid's speed, vf, when it reaches the Earth's surface. All right, so we're trying to find what basically, we're going to have to use conservation of energy. We want to find what the kinetic energy of this asteroid is going to be when it hits Earth's surface. And we're just going to neglect the atmosphere having any effect and slowing it down or anything like that. All right, so because we're to neglect the effects of the atmosphere on the asteroid, the mechanical energy of the asteroid or system is conserved during the fall. Thus, the final mechanical energy, when the asteroid reaches the Earth's surface, is equal to the initial mechanical energy. With the kinetic energy K and the gravitational potential energy U, okay, we can write this as, so our initial mechanical energy is just going to be the kinetic plus the initial potential is equal to the final. So the final kinetic plus the final potential. All right, so this is just our conservation of energy. So also, if we assume the system is isolated, the system's linear momentum must be conserved during the fall. Therefore, the momentum change of the asteroid and that of the Earth must equal in magnitude and opposite in sign. However, because Earth's mass is so much greater than the asteroid's mass, the change in the Earth's speed is going to be negligible relative to the change in the asteroid's speed. So the change in Earth's kinetic energy is also going to be negligible. Right, so basically, if the change in momentum is going to be negligible for the Earth, the change in kinetic energy is also going to be negligible. It's going to be a very small number. So thus we can assume that the kinetic energies are those of the asteroid alone. Right, so that's really all we're going to be worried about. All right, so we can let m represent the asteroid's mass and big M represent the Earth's mass. The asteroid is going to be initially at a distance of 10 times the Earth's radius, and then finally a distance of 1 times the Earth's radius, right, where the Earth's radius is given. All right, so we know that the potential energy and the kinetic energy, we can rewrite this all. Basically, we're just plugging in for our first equation here. All right, so our initial is going to be 1/2 mv naught squared. Well, this would be initial. Minus the potential energy, which is going to be gm times the mass of, we'll just use little m for that, divided by 10 times the radius of the Earth. This is when it's far away. And then finally, when it's crashing into the Earth's surface, it's going to have some final velocity. And it's also going to have some potential energy still, but it's only going to be 1 times the Earth's radius. All right, so it's going to be a little bit larger. All right, so the final velocity, basically what I want to do then is solve for this final velocity. I can realize that there's a little m in each term, so the little m's are actually going to cancel out, and that simplifies things quite a bit. So our final velocity ends up being, basically what I'm going to do is solve for this, so I'm going to add this term to the other side, then I'm going to multiply both sides by 2, and then I'm going to take the square root. All right, so doing this all in sort of one step, you end up with 2 times the first part, which is 1/2 v naught squared minus gm over 10 times the radius of the Earth plus gm over the radius of the Earth. Then you're going to plug in all the values that we know. So we know that it's going at 12 kilometers a second, so you're going to want to convert that to meters a second. Plug that in for our initial velocity. All right, this is going to be the mass of the Earth, then the radius of the Earth, and so the same for the second term then. So our final velocity ends up being 1.60 times 10 to the 4th meters a second, which is about 16 kilometers a second. All right, so the asteroid is going to basically hit the Earth at 16 kilometers a second. And it gained energy, which makes sense because it's going to be, it gained kinetic energy, right? Because it's going to be losing some potential as it gets closer to the Earth. So at this speed, the asteroid would not have to be particularly large to do considerable impact or damage at impact. If it were only 5 meters across, the impact could release about as much energy as a nuclear explosion at Hiroshima. Alarmingly, about 500 million asteroids of this size are near Earth's orbit, and in 1994, one of them apparently penetrated Earth's atmosphere and exploded 20 kilometers above the South Pacific, setting off nuclear explosion warnings on 6 military satellites. So the impact of an asteroid, 500 meters across, there may be 1 million of them near Earth's orbit, could end modern civilization and almost eliminate humans worldwide. Right. I love how cheery some of these examples can be. Okay. So we're going to stop here. There's going to be one more lecture that finishes up the chapter. It's going to discuss Kepler's law and then a little bit more about energy.